Okay, solid state chemistry. First one, solid state chemistry. We know that is state of matter are basically three types. One is solid, other is gas, and other is liquid. Okay. Their attraction force between molecules, that should be more in solid, then liquid, then gas. Okay. And we know solid having their definite shape, definite geometry, and their force of attraction between molecules or atoms, that should be high or highest among liquid, gas, and solid. Okay. First one, for solid state we have to consider distinction between crystalline and amorphous. Solid are basically, okay, that is states of matter. That should be, one is solid, other is liquid, and that should be gas. Okay. Solid have definite, okay, now we come solid. Solid have definite shape, geometry, and their attraction force between atoms highest. Okay. Solid, their definite shape and geometry, okay, and their attraction force between atoms and or molecules, that should be highest. Okay. Then again, if we consider their force of attraction between molecules or ions, that should be more in solid, then liquid, then gas. Okay. Solid, then liquid, then gas. Okay. Now we consider example. If we say that is example, it should be clear. That is like, for example, solid. That should be as for example, as we know, that is ice, that should be solid state. Okay, ice, that should be solid state. That should be ice. We can know that is NaCl crystals are also solid. Okay, so many are there. Okay, now we consider solids are type of solids. Solids are basically two types. One is amorphous, other is crystalline. Okay, that is, one is amorphous, other is crystalline, and their properties are defined. That is, crystalline, obviously crystal like structure can be there, amorphous like powder like structure. Okay, now we consider distinction between crystalline and amorphous solid. Okay, nature, crystalline have definite and regular arrangement of constant or particles in space. Means they are regular arrangement. There should be normally no deviation. Okay, they are perfect arrangement. And amorphous does not have any regular arrangement. There must be no fixed arrangement can be there. They there are no fixed arrangement. Okay, so constant particle in space, that should be called amorphous. Okay, crystalline, as they are perfect arrangement, so we can term as true solid. Okay, amorphous and there must be no perfect arrangement, so we cannot say that is a true solid. Amorphous solid considered as supercooled liquids or pseudo solids. Pseudo means we should be show as solid character but having loss of many characteristic of solid. Okay, arrangement, there should be long ordered in arrangement of the particles in crystalline structure, and amorphous there should be short range arrangement can be present. Okay, crystalline and isotopic in nature means their physical and physical properties are defined in defined direction. Okay, that's why that is called anisotropic. So as isotopic, that should be anisotropic. Okay, and amorphous, that should be isotopic because their physical properties are same in all direction. Okay, all direction means this, that should be x like that, this direction. Okay, anisotropic means their physical property that should be defined in defined direction, but isotopic means their physical properties are same in all direction. Okay, melting point, crystalline having sharp melting point, amorphous having certain range of temperature, that should be, there should be range, as for example 5 to 25 degrees centigrade, like for example. Okay, cleavage, that is crystalline undergo clean cleavage when they should be cut. There must be clean cleavage. Like for example, there should be this type of cut can be there. Like for example, but there should be irregular. That is, as for example, A, B, C. There should be cut this. That should be irregular. Okay. And crystalline, that should be heat of fusion. Definite and characteristic heat of fusion can be seen. Amorphous do not have definite heat of fusion. There must be no definite heat of fusion, means variety of can be seen. If we consider experimentally if we study experimentally about amorphous solid, we get various value at defined times at defined condition. Okay, so there must be no fixed amount of heat of fusion. Okay, now we consider solid. If we consider their force of attraction and in concept of bonding, they should be divided into three categories. That should be ionic, that should be covalent, and there should be coordinate. Okay, ionic, covalent and coordinate in concept of bonding. Okay, or their participation in bond formation. Okay, that is character. First one, constituent particle. Ionic solid, that should be consist of positive and negative ions. As for example, Na plus and Cl minus. Okay, Na plus and Cl minus. They are due to force of attraction, that is electrostatic force of attraction among cations and anion that should be produce ionic compounds or iodine solid. Okay, that's why consider particle that should be positive and negative ions. Okay, covalent network solid that should be consist of atoms. Atoms means why? Because there must be no chance of formation of cation and anion. There should be only possible mutual sharing. As for example, hydrogen 1 electron donor, hydrogen 1 electron donor, that should be bond formation. Mutually they count the bond, and by this way H2 molecule can be produced. Okay, that is called covalent bond. Okay, there should be chance of mutual sharing, because there must be, if H minus is produced or H plus are produced, both are reactive, they are not stable, they are reactive. So they always, they are reactive, but we can use, that is H atom and combine it by mutual sharing, that is H2. Okay, that is more can be explained by carbon containing compound. Carbon having outermost shell 4 unpaired electrons. Okay, so if we consider carbon as a cation, there should be removal of electron can be take place. That is for carbon 4 electron removal is very tough. Okay, to produce cation, or and if we consider that is for fulfilling octet anion, there should be 4 electron put in the outermost shell of carbon, that should be also tough. So for this case, carbon bears the intermediate pathway, that should be mutual sharing. There are 4 electrons that should be mutual shared by other atoms to produce maybe single bond, maybe produce double bond, or sometimes triple bond also. Okay, as we know, carbon having no vacant d orbital, so it cannot extend its octet configuration. Okay, now we consider second one, molecular solid. That should be molecule that should be are solids, basically their London force, van der Waals force can be existed. Okay, and metallic solid, this molecular solid that should be consist of molecules. Okay, and metallic solid that should be consist of positive metal and their kernels, which can be have free electrons. Okay, there should be interaction of metal and their free electrons. That is called metallic solid. Okay, so that's why metallic solids are good conductor, because there should be free electrons, and free electrons are permissible to carry electricity. Okay, next one, bonding force. Ionic solid, there should be electrostatic or Coulombic attraction. As we know, when cation and anion are produced, so there should be electrostatic or Coulombic force of attraction can be generated. Okay, and covalent network, there should be covalent interaction, means they are covalent, they attach, we can say this force of attraction covalent force. And molecular solid, that should be van der Waals force or dipole. Maybe sometimes there should be dipole can be generated. That's time we can say dipole interaction can be occur. Okay, and metallic solid, there should be completely defined, as there must be actually metal and electrons are present, so that is not same to all the types, that should be defined types. So that's why there should be metallic bonding can be present. Okay, melting point, ionic solid that should be high, covalent that should be very high, and molecular solid that should be low, and metallic solid that should be moderate to high. Okay, physical nature, that is ionic solid are hard and brittle, because their attraction force are too much, so they bind to each other with more force. Okay, so they are hard and also brittle. And covalent and network solid, that should be very hard, mutual sharing is there, they do not cleave their bond. Need to cleave the bond, we have to provide some energy, that's why. And molecular solid, that should be very soft. Okay, their interaction are weak, as dipole interaction and van der Waals force both are weak, so we have to give small energy, small amount of energy, so that's why very soft. And metallic solid, hard but malleable. Okay, conductance, ionic solid conduct in aqueous solution, molten state, but insulated in solid state. Why? Because in aqueous and molten state they furnishes cation. Okay, and they both of it can carry electricity, but in solid state they does not produced. Okay, in solid state Na plus and Cl plus does not produce, so they are insulator on that time in solid state. Okay. Now covalent or network solid, that should be non-conductor. Why? Because there must be no chance of ion furnishing tendency, or no chance of free electron finding probability. Okay, so we can say covalent or network solid are non-conductor. Okay, molecular solid, that is also insulated similarly, because there should be no chance of cations, anions, and no chance of electrons, that should be we find. Okay. Metallic solid, that should be good conductor, because there should be free electrons, and that should be responsible for carry of electricity. Okay. Now we go example, that is ionic solid, NaCl, CaF2, calcium fluoride, magnesium oxide, MgO, ZnS, zinc sulfide. And covalent or network solid, that should be diamond. We know diamond structure, the allotropes of carbon. One type of allotrope of carbon where all CC single bond are exist, and that should be most harder material, we can say. Okay, and that is very price is so high. Okay, and silica, SiC, so on. Molecular solid, as for example, water, carbon dioxide, carbon tetrachloride, CCl4, HCl, hydrochloric acid, and SO2, sulfur dioxide. Okay. Metallic solid, that should be copper, Fe, Ag means silver, and magnesium. Okay. Now we come Bragg equation. Okay. Bragg equation means what? That is, there should be crystal, incident ray come, okay, and reflected beam, that should be go. Okay, and their bond angle, this. Okay, this and this. Okay, that should be their incident angle and reflex angle, that should be equal. Okay. So always remember, there must be two phase, we can say. For constructive interference, that is, the path difference is in lambda. Okay. And for destructive interference, that should be in lambda by 2. Okay, for constructive interference, path difference is in lambda, and for destructive interference, path difference is in lambda by 2. Okay, but normally, generally we consider constructive interference, so we can say 2d sin theta equal to in lambda. Okay, 2d sin theta equal to in lambda. That is called Bragg equation. Okay, that only be seen for solid state. That is in lambda 2d sin theta. High temperature, cohesion number increases. High temperature, the cohesion number decreases. Okay. N equal to 1, 2, 3. That is integral number, diffraction order. Lambda is the wavelength of X-rays incident on crystal. Nothing but incident ray, the wavelength of incident ray. Okay. This is the distance between atomic planes, and theta is the angle at which interference occur. Okay. The angle. Okay. Now, we consider there should be so many types of unit cell can be there. Unit cell means the simplest the simplest unit that should be repeating arrangement to produce a bigger crystal. Okay, there should be 4 types are common. First one, simple or primitive unit cell. There should be means the atoms are present at corner. Okay. That is the number of particles and their contribution, that should be total particles 8, and their contribution 1 by 8, that is ultimately 1. That should be called Z. Okay. And next one, face centered unit cell means there should be corner and there should be face. Okay, face having also some particles. So there should be face, total face 6 and 6, their contribution half. So 6 into half plus total atoms at corner, that should be 8, into their contribution 1 by 8, ultimately we get 4. Okay, that should be Z value. Okay, that is TPP value. Total, that is, I think not. Z value is defined. Z value can be used in density formula. Okay. Okay. Next, body center, there should be at corner also present and at center that should be present. Okay. There should be the contribution, that is corner, all corner atoms, total corner atoms 8 and their contribution 1 by 8 and plus 1, that is for body center, equal to 2. Okay. Then end center, there should be only 2 faces, atoms are present and also corner. Okay. So for 2 faces, that is face 2 into their contribution half, that is for 1 and plus total corner atoms 8 into 1 by 8, that is should be 1. So 1 plus 1, 2. Okay. Now we consider packing fraction. Okay. First one we consider if, that is different balls are arranged like that, they are linearly arranged and one atom placed top of the other atom, like this type of arrangement if we draw or if we arranged. So on that case there should be some empty space can be there. Okay. Cohesion number, that should be 4 because that should be square. 4 atoms are surrounded by the central atom. That's why cohesion number 4. And there is always AAA type arrangement. Okay, space occupied. By sphere, there should be the packing fraction, that is 52.4%. Okay. Okay. Now we consider hexagonal close packing. If by this way, that is one layer that should be oriented in their middle intersection point, we draw other layer. Then again their intersection point, we draw other layer. By this way, we can produce hexagonal close packing, AB type. And space occupied sphere, there should be not packing fraction, that is a space occupied. Okay, 52.4%. And that should be space occupied sphere, that is 60.4%. And that should be more efficient. Why? Because their emptiness decreases. Their emptiness, that should be decreases. Okay, that's why their packing, that is more effective. Okay. Okay, now 3-dimensional packing of constitutive particle, that is AAA, and that should be 3-dimension. Now 3-dimensional close packing form 2-dimension. Now we consider 2-dimension. First one, hexagonal close packing, that is ABEB type. 74% space that should be occupied. I think this 60.4, 74, that should be packing fraction. Okay. And cubic close packing, that is ABC type. Cohesion number of HCP, that is hexagonal close packing, and CCP, that is cubic close packing arrangement, is 12. Their cohesion number, that should be 12. And while in BCC cohesion number, that should be 8. Okay. Now close packing of atoms in cubic structure. Close packing of atoms in cubic structure, that is the order is FCC, face-centered cubic lattice, then BCC, that is body-centered cubic lattice, then simple cubic lattice. Okay. All noble gases have CCP, that is cubic close packing structure. Okay, except HCP structure. Helium, that should be exhibit in HCP structure. All noble gases, that is helium, neon, argon, xenon, krypton, radon, we know that except helium, all are belong to CCP structure. But only helium, that should be exhibit HCP structure. Okay. Now we consider void or space or holes, means emptiness. Okay, their empty space that should be present. In trigonal void, we consider there should be a trigonal void present. Okay, that should be this type of trigonal void present. Okay. Now tetrahedral voids, question number 4, there should be tetrahedral voids, and R void, the radius, that should be 0.225 into R square. R void equal to 0.225 into R square. That should be used for numericals. Okay. Now we consider octahedral voids, that should be question number 6. That is octahedral voids, R void equal to 0.414 into R square. 0.414 R square. The number of octahedral voids present in a lattice is equal to number of close packed particles that should be there. Okay. Number of octahedral voids is nothing but equal to that is number of close packed particles. How many particles are present equal to number of octahedral holes. Okay. And the number of tetrahedral holes present in the lattice, that should be twice of the number of close packed particles. That should be, if n are octahedral voids or n are the close packed particles, then 2n is the tetrahedral holes. Okay. Now primitive cubic unit cell, that should be, if we consider primitive, this there should be, that is the distance, like for example, okay, this type of structure, if there must be corner are present, we can say this and this. There should be the distance d equal to 2r. Okay, d equal to 2r, and as their radius, that should be the cubic length, that should be a. Radius is r and cubic length is the a. That must be r equal to a by 2, means 2a equal to r. 2a, sorry, that is 2r. As there must be 2 atoms are present, so that is 2r equal to a. Okay. Now packing fraction equal to volume of atoms, and by volume of cubic unit cell, that should be 4 by 3 pi r cube. Small r cube, r is the radius of the particle, that should be volume, by 2r cube, that is radius that cube, that should be 0.524. If we use as a percentage, that should be 52.4%. That should be percentage. Okay. Okay. Face centered cubic unit cell, that is d equal to a root 2. Okay. R equal to root 2 a by 4. Packing action 4 into 4 by 3 pi r cube by 4 r by root 3 the whole cube, that should be 0.74 or 74%. The packing fraction of HCP and CCP structure also 74%. Okay. Last one, body center, that is d equal to root 3 a by 2. That's the length of body diagonal root 3a. That is r equal to root 3 a by 4. Packing fraction 2 into 4 by 3 pi r cube by 4r by root 3 whole cube, that 0.68 or 68%. Okay. For cube, always remember this diagonal, that is a, that should be a triangle. So a square plus a square, this triangle x square, that is x equal to root 2a. Now we consider body diagonal, that should be body diagonal. That is must be what we say, if we consider this structure. Okay. This. Okay. This body diagonal, there should be considered some angle. Okay, that is must be root 2a, that is must be a, that is root 2a whole square plus a square equal to x square, equal to x equal to root over 2a plus a, that is root 3a. Okay, that is should be body diagonal. Okay. So we get that is face diagonal, that is root 2a, and that is body diagonal, that should be root 3a. Okay. Now we consider if that should be cube, not a cube. Cube, there should be, if we consider they are face diagonal, and ultimately we can say that is if this space can be occupied, there one atom, there should be one, that is ultimately 2r. Okay, that is must be root 2a equal to 2r, that is r equal to or a equal to 2r by root 2, right? We can say for FCC. Okay. For BCC, that is a body diagonal. This is okay. That is must be 4r equal to root 3a. Okay, a equal to 4 by root 3. Okay, that is 1r, 2r. Okay, r plus 2r, then again r. That should be 2, 1, 4r. Okay. 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 By this way we can say, sorry, r equal to root 3 by 4a also. Okay. Now we consider density of unit cell, that is symbolized as D. Density of unit cell equal to mass of unit cell by volume of unit cell. Mass of unit cell by volume of unit cell. The density of unit cell is same as the density of the substance. Density of a cell, that should be same is density of substance. D equal to Z small m by AQ. M is the mass. But we also consider mass of an atom small m we cannot determine. So mass of an atom small m equal to capital M by Na. Na is the Avogadro number, that is 6.023 10 to the power 23. That should be Na value. Okay. So we can say Zm Na cube kg per centimeter cube. Okay. That is D is the density of unit cell. M is the molecular weight, Z is the number of atoms per unit cell, and Na is the Avogadro constant, A is the edge length of the unit cell. How we can memorize it? That should be Jamna. Okay. J for Z, M for M by N for N, A for A cube. Okay. Jamna. Okay.